Hello, this is the assistant to Dr. Sniley speaking. In the last phase we have produced something like this, which is great and terrific, but not exactly what we want. So it seems there is some sort of overflow, and I guess we might want to prevent that from happening in the first place. And how does one fix a numerical overflow? Of course, you check for it and make sure you scale or truncate the value accordingly instead of just taking it as it is. As you can see, we just clamp pixel values in the right next pixel method where it all happens. And voila, this is how it looks like. Kind of expected because we just fixed symptoms after all, white spheres. So this means that the high value is coming from somewhere and there are not too many possibilities even. Let's have another look. Let's have another glance at the Ceepepporg version. The light there, it is unitized, right? And if I remember correctly, our one is not. I don't have to remember that, I just look at it to see that we are not normalizing our light. So if we do that, something good should happen to us, right? And yeah, it's not an omni-light. You know, I thought it was an omni-light, but of course it's not an omni-light. It's just a directional light because it's normalized. The only thing that matters is the direction. And this explains why the dot product between the two vectors has been way too large for us. It should be only from 0 or -1 to 1, depending on the orientation of the vectors if these are unit vectors, so they have to be normalized. Anyway, look at that. Gorgeous. That looks like something is happening. So the shading is not off the charts anymore, just from white to, well, dark or black. Awesome! One great fix done. But of course we are not quite there yet. I think I could verify that the sphere intersection is correct just by having proper test cases for that very simple implementation. But the group implementation is a bit more complex. And first of all, it seems that I'm using the incorrect I'm not handling max distance correctly because I'm testing against infinity, even though I should use the max distance there. Something else that was fixed in the meanwhile is the way it intersects for its members, because previously it would abort on the first hit, even though we have to find the closest item to the ray, right? So we have to go through all of our members, no matter what. Something else we fixed in the meanwhile is the logic here, which was inverted. Previously we checked if there is a hit, and then we did some shading, which explains why our shadows kind of showed shading, whereas they shouldn't. What you see here is yet another logic error, because of course, if there is a free side to the light, then we want to do the shading, otherwise we don't want to do any shading. Yeah. So in theory, that should work much better now. Let's see. Okay, just compiling and rendering, and there we go. That was quite fast as well, not bad. Looks much better than before. I think it could be very close to our comparison image even. Look at this. I mean, sure, it's still flipped and whatnot and wrong sides, but that is minor. Good. What else is wrong? It seems like, sure, it's upside down when we render it, and it seems to be sort of moved to along X a bit, right? So there must be a 1 somewhere where there should be a 0. So maybe it's this one. Yeah, let's first have a look on the left side if there is a 0 or a 1. And it looks pretty much like there is a 0. Okay, so let's put a 0 there in our place and go again. There we are. Now the spheres are centered. Awesome. We are really close now. So just the inverted image left to be fixed. But first things first, let's have a little intermediate benchmark, shall we? So the CPP version does it in 0.601 seconds, or 0.5, well, let's say 0.6 seconds. It's 1024 by 1024 with one sample. And how much do we do? I'm not sure why it takes me so long to verify this, because I think I should just be able to do a make image, but no, I do it manually. Here we go. So we do the same thing in 0.457 seconds. Wow. So we seem to be faster, right? I just put a big question mark here because usually it's really difficult to be faster than CPP. But maybe we are, because our implementation is so much better. I don't know, I doubt it. I'm just the assistant. But let's see where that leads us. But honestly, before more work is done on anything, I'd rather get this code a bit more, well, a bit easier to read, because all of this type T is float trait thing. It was an interesting experiment, but I think the experiment clearly failed, or, well, there are better ways or easier ways to do this. There must be easier ways, so let's get rid of this so that we can use floating point literals once again directly in our code. Moving swiftly on, let's have a look if all that fuss about 32 and 64-bit floats makes a difference, right? So with 64-bit floats, it takes 5.07 seconds, 0.507 seconds, and with 32-bit floats, it's 0.46. So definitely, it's marginally faster to use standard position floating points instead of double position. Was kind of expected, and we are not too floating point heavy either, so it's not too much happening there. Most of the time we're iterating arrays of members, I guess, and that's pretty much it. So yeah, 32-bit should be fine for us. Let's move on. I was me if I wouldn't get a little bit carried away, because instead of making it work right, like flipping the image upside down, I decided to run some Wahlgrind, core grind, just to see how fast it's going or where I'm spending all my time, because I thought maybe there's a little bit of potential to improve performance even more. Turns out that intersect, who would have thought that, is the function called most of the time, or the method should I say, and right now it's not the most efficient because it has a big return value, which is an optional that we have to decompose or destructure, and. So if you would improve that, we could certainly save a lot of time. So right now I'm just passing a mutable hit. The hit carries a distance, the distance is used as max distance, and if we are valid, basically if our distance is below the max distance in the hit, we will return or we will change the existing hit that we get there. That way we basically save a lot of writes to memory and simplify the whole thing quite a bit. And let's see what we have here. Compiling, rendering 0.41 seconds. Awesome, that's quite a new record, I suppose. Well, that was quite a successful day. It all works, and not only that, it also works fast. Right now we are definitely faster than a C++ implementation, even though I must admit we have changed the algorithm to a point where we are just more efficient because of a slightly better signature of the hit function and such. So I guess at some point we will have to schedule kind of improving the Ceepepporg and possibly even the Gopher implementation somehow. But that and more will be done in the next phase. I'm off for today and see you tomorrow.
That and more in our next episode of Trace Quest 5.